Today we will discuss mainly the petrochemical products. Petrochemical products, we know the polymeric materials are all petrochemical products. So petrochemical products, what kind of products it is and how it is derived from the petrochemical industry. And also we will explain about what are the classification of different petrochemical products and their characterizations. So let's see. This is a total scenario of refinery and petrochemicals industry. You see, in the petrochemical industry, what are the feedstocks? Either naphtha or gases. And those naphtha and gases comes from the refinery unit. Refinery unit gives the naphtha, and the naphtha is being used in the petrochemical industry as the feedstock material, the main feedstock material. Apart from that, some gases are also used because petrochemical industry by nature it may be naphtha cracking unit, it may be the gas cracker units, isn't it? So accordingly, either gas or naphtha is being cracked at the petrochemical industry at the beginning, where from the other materials are generated for making the finished product polymer. So you see the refinery unit, refinery is nothing but a distillery unit. So by the refinery unit condensate, by the distillation, the naphtha fractionate is taken out from the distillery, from the refinery unit, and then it is sent to the heart of the petrochemical industry, that is the cracker unit, where it is cracked. Not only that, some butane may be cracked. What I told that not only naphtha, some gases are also used because by the nature of petrochemical industry, initially in Indian scenario if you see. So initially when the petrochemical industry was set up, that is Nosil, Peel, these are the famous petrochemical industry initially established in the industry. And those petrochemical industry were based on the cracker unit. But currently the scenario has been changed. Naphtha was used, naphtha is being used as the main feedstock for petrochemical industry. But now the current trend has been again changed. The latest technology in petrochemical industry, they are also trying to use the gases as their feedstock. Some advantage, disadvantages are there, and that will be explained later. Now you see, if we consider the petrochemical industry, the main cracker unit which is thermally cracked, the naphtha gases are cracked thermally and utilizing steam. And what kind of products are coming out from the cracker unit? One is ethylene, propylene, butadiene, and pi gas stream is there. And what is the contents of the pi gas unit? Pi gas unit is basically having all aromatics. The major aromatics, that is benzene, toluene, and xylene. So accordingly, the petrochemical products have been classified into three major categories. One is first generation petrochemical product, second generation petrochemical product, and third generation petrochemical product. What is first generation petrochemical product? First generation petrochemical product are considered those products which are directly coming out from the cracker unit. Means when naphtha is used as the feedstock, after cracking we are getting ethylene, propylene, butadiene, pi gas, that is aromatics. Some alkanes are also coming out. So these are called the first generation petrochemical product. For example, you see methane, alkane stream, methane, ethane, propane. Then alkene stream, ethylene, propylene, butylene, acetylene, butadiene, aromatics, benzene, toluene, xylene, as I mentioned. Second generation, when the first generation petrochemical product are chemically modified to some extent. These are called the second generation petrochemical product. For example, the final product, polymeric product, say polyvinyl chloride, PVC, is a very common and very popular commodity plastics. The PVC is what is the raw material for making PVC? Vinyl chloride. But that vinyl chloride cannot be directly obtained from the cracker unit. So we need a intermediate treatment. So when vinyl chloride is produced by an intermediate treatment, that is called second generation petrochemical. So basically second generation petrochemicals are the derivative of first generation petrochemical product. Few examples: styrene. Styrene is popularly used for making polystyrene, but styrene cannot be obtained directly by the cracking of naphtha or cracking of gas from the cracker unit. So styrene is derived from benzene and ethylene. You see, the benzene and ethylene both are first generation petrochemical because these benzene and ethylene are directly obtained by the cracker from the cracker unit. But when that benzene and ethylene is reacting together, we get styrene. So styrene is considered as the second generation petrochemical product. Similarly, dimethyl terephthalate. Dimethyl terephthalate, you know, this is one of the important precursor for making polyester. But dimethyl terephthalate we cannot get directly from the cracker unit. It is derived from paraxylene. But paraxylene is obtained directly from the cracker unit. Paraxylene is the first generation petrochemical product, but dimethyl terephthalate is second generation petrochemical product. Similarly, other examples are there like ethylene glycol, vinyl chloride monomer, adipic acid, acrylonitrile. These are all considered as the second generation petrochemical product. And third generation petrochemical product are all polymeric product, which is the finished product from the petrochemical industry. All the virgin polymeric materials are considered as the third generation petrochemical product. And after that, the downstream consumers, they are taking those virgin polymers from the petrochemical industry. Then they are using that polymer for making their finished object of polymeric material. So that is polyethylene, polypropylene, polyvinyl chloride. After polymerization, that polymer all polymers are known as third generation petrochemical product. But in the meantime, another one thing I would like to mention here, that in the aromatic stream, that which is coming out after naphtha cracking, after gas cracking. So particularly for naphtha cracking, that aromatic stream is very enriched. Here also you see what we are getting: benzene, toluene and xylene. That benzene is further processed to cyclohexane, caprolactam and nylon 6,6. So here benzene in the aromatic stream, that is pi gas stream, that benzene is considered as a first generation petrochemical product, whereas the cyclohexane, caprolactam, these are called second generation petrochemical product, and nylon 6,6 is the third generation petrochemical product. Similarly, toluene, xylenes are considered as the first generation petrochemical product, and when it is further processed to toluene diisocyanate, this is second generation. Similarly, xylene, orthoxylene, two isomers are there. Orthoxylene, it is processed to phthalic anhydride, second generation. Paraxylene, it is further processed to purified terephthalate, PTA, pure terephthalic acid, purified terephthalic acid. These are called second generation petrochemical product. A few examples of third generation, all polymeric material or polymeric products, polystyrene, polyvinyl chloride, azodyes, DDT. Now come to the classification of different polymeric products. There are several bases for classification. As per origin of the polymeric material, we can classify as the natural polymer, synthetic polymer, and semi-synthetic polymer. Natural polymers means polymeric material which are naturally occurring. Natural rubber, proteins, carbohydrates, these are all natural polymers. Semi-synthetic, when the natural polymer is chemically modified. One common example I would like to mention here, that cellulosic material. Cellulose is actually, cellulosic material comes from the trees. And when the cellulosic material is chemically treated and it is regenerated, then regenerated cellulose, its market value is further increased, and it is popularly used for making fabrics, isn't it? That silk, poor man silk, it is very common, known as poor man silk. That is regenerated cellulose. So that is actually derived from the raw cellulose, raw cellulosic material. So this is semi-synthetic. And synthetic is absolutely which is produced in the petrochemical industry fully. These are synthetic. Thermal response wise, the polymeric material can be classified as into two categories. One is thermoplastic, another one is thermosetting. Thermoplastic means thermally, actually its behavior towards the thermal application. The polymeric material, the plastic material which can be remelted, means after giving the final shape of product, it is possible to remelt and to reshape. So that is called thermoplastic. For common plastics means polyethylene, polypropylene, these are all thermoplastics. And these are recyclable, because you know the old materials, old polymeric objects are sold in low price, and they are being recycled back to give the reshape of the product. But thermosetting plastics, thermosetting polymers or thermosetting plastics, they cannot be remelted. For example, the switchboard, in the switch material, that is urea formaldehyde, phenol formaldehyde. Once the final shape is given, it cannot be remelted by the thermal application. So that is the limitation for thermosetting polymers. But it has some advantages also. The thermosetting polymer can withstand very high temperature, isn't it? So that's why it cannot be melted. Similarly, mode of formation wise, means if you look into the mechanism of formation of polymer, because basically these are chemical reactions. All monomers are chemically reacted together and product polymer is produced. So depending on the mode of reaction, the product polymer can be classified into two categories. One is addition polymer, another one is condensation polymer. So the monomers, those are having unsaturation. They are generally formed polymer by addition mode. Polyethylene, polypropylene, where ethylene, propylene, these are raw materials used. These are monomers used, and all those monomers are unsaturated. So their mechanism, their formation mechanism is different to that of the mode of preparation, where the monomers having no unsaturation, but they are having functional groups. So when they are reacting together, their reaction is going through their functional groups. So these are called condensation process. For example, polyester. nylon. These are all condensation products. Structure-wise, polymeric material can be classified into three major categories. One is linear. Linear means structure means polymer molecular structure. Polymer molecular structure that can be linear, can be branched, can be cross-linked. I am coming later. Mode of application wise, the rubber, plastics and fiber, and the tacticity wise, isotactic, syndiotactic and atactic. Crystallinity wise, either crystalline or non-crystalline, and another one is amorphous. So non-crystalline, crystalline, semi-crystalline. Non-crystalline is amorphous. So you see, thermal response I have already, this is the mode of formation. You know the addition polymers where the monomers are unsaturated. These are used for addition polymerization process and condensation polymerization process where functional groups are there. Addition polymerization proceeds through three different stages. One is initiation stage, and then propagation step, and third is termination step. Initiation step, in presence of a suitable initiator, the unsaturated monomer is started polymerization, where the initiator provides, and it is absolutely a free radical mechanism. That free radical is initially being supplied by the initiator. So once initiator supply radical, then the polymer, it will attack to the monomer, and the second monomer will be linked with the previous monomer which is having already one radical, isn't it? So this one first one stage is called initiation stage, second is propagation. In the propagation stage, successive monomers are being linked together, and one time will come when we have to stop the polymerization process, because whenever we are going to produce any polymeric product, we have to be very much careful about its molecular weight, its structure. These are all to be maintained. So here actually you see when the chain propagation is started and monomers are being added into it in succession, then one time will come when we have to stop further polymerization process, and that step is called termination. And termination step, there are several mechanisms. Termination may be there in presence of a suitable third component which is called short stop agent or chain transfer agent, isn't it? But if we look into the mechanism of termination, so two propagating radicals bearing free radical each, they can combine together. So in this kind of termination is called termination by combination. And if one radical bearing chain provide or transfer its radical to another one, then this is called disproportionation. This is, you know, the chemistry in the reaction by nature of reaction, either is combination or disproportionation. Characteristics should be there in the addition chain polymerization, condensation, step polymerization process. It has its own characteristics, like as I mentioned, addition should be unsaturated monomer, it should be functional group. Monomers add to give a polymer and no other byproduct is formed. But in, you know, the condensation process, condensation reaction, always a byproduct is there. So whenever condensation polymerization is taking place, one byproduct should be generated there. And number of monomeric units decreases readily throughout the reaction. obviously with time the monomer will be consuming with time. So the concentration of monomer will be gradually decreasing in the system. Similarly, in case of condensation polymerization, the number of functional groups that will be decreased with time. Molecular weight of the polymer will be gradually increasing because the number of monomers are being added into it. So the molecular weight of the polymeric chain will be gradually increasing. High molecular polymer is possible to form in this addition polymerization process, whereas in condensation polymerization process that much high molecular weight is not possible. Longer reaction times gives higher yield but have a little effect on molecular weight. Thermoplastics are produced, for example polyethylene, PVC, as I mentioned. Copolymerization is another one type. Copolymerization is when more than one type of monomers are used. That is for making the polymer. That is called copolymer. Copolymer more than one type. So for example, see here two monomers, M and N. The two monomers are being used for making the polymer. So what would be the fashion of linking? Depending on that, the types of polymer will be produced. One, if the fashion is just alternating fashion. See here M and N, two monomers are used. Okay, so M and N, they are linked together in alternating fashion. So that product of copolymer is called alternating copolymer. Similarly, block copolymer, when the same type of monomers are linked for some time. So few same type of monomers are linked together, then another type of monomers are linked together for some time. So in this way they are producing a same type of monomer block at the whole chain. So this kind of polymer is called copolymer, rather it is called the block copolymer. And grafting copolymer is different. One monomer is utilized for making the main backbone of the polymeric chain, and the second type of monomer is utilized for making the branch, because every polymeric molecule will have some degree of branching. Nil branching is almost not possible for high molecular weight polymer. For small molecular weight polymer, it is possible to produce without any branching, but high molecular weight polymer should have some degree of branching, but it should be regulated, well regulated. So it comes, what will be the structure? The structure, linear structure, as I mentioned, the structure wise also you can classify the polymer. So structure wise is a linear polymer. Linear polymer means its structure is linear throughout. Okay, branched, you see this one, this is the main polymer backbone, and this one the branching. This is branched polymer. And cross-linked network structure. Cross-linked means these are the polymeric material, polymeric chain, main polymeric chain, and which are interlocked. This is called, this kind of interlocking system which leads to the formation of polymer network. Appearance wise, you know, rubber, plastics, fiber. Rubber means if the structure is low mechanical strength, dimensionally unstable, and the degree of crystallinity is also the main parameter for classifying rubber, classifying plastics. And fiber, in case of fiber is a class of plastics. But thing is that in case of fiber making polymer, it should have the minimum branching, and not only that, its molecular weight should be sufficiently high compared to other two groups. Tacticity, as I mentioned, tacticity mentioned due to orientation of the branching, orientation of the functional groups. Depending on that, the structure of a polymeric chain is being classified, because the branching, degree of branching and its alignments dictates the properties of the finished product polymer, isn't it? So accordingly to the orientation of the branching, orientation of the functional groups along the main chain of the polymer, that either isotactic if the alignment is one-sided, symbiotic it is the alternatively aligned, and atactic it's a random alignment there. Because why it is required to know? Because it will be the main cause of its crystallinity. Because if we consider, say, polyethylene is a popular commodity plastic, very popular commodity plastics. All petrochemical industry are producing polyethylene, and different grades of polyethylene: high density polyethylene, low density polyethylene, linear low density polyethylene. And what is the differences? The differences are mainly on their molecular weight and their crystallinity, their density. That this density is the result for differing their crystallinity, differing their molecular weight. Okay, so these alignments means the tacticity is playing the vital role for defining its crystallinity, defining its density. And in case of the tacticity, if the tacticity is regular one, then obviously we can get our desired crystallinity, we can get our desired density. Mostly isotactic, symbiotic structure gives higher density, higher crystallinity, which is actually the result of making high density polyethylene. But in case of low density polyethylene, the structure is not defined, structure is not regular. And amorphous structure, amorphous structure means there is no crystallinity. So crystal, how can we make it? How can we describe the crystallinity of a polymeric product? So at least it should be more than 60% crystallinity is there. Otherwise we cannot say it crystalline. Okay. So rubber material is not crystalline, amorphous, because crystallinity is not there. Now come to why polymer is produced. Polymer is produced, the virgin polymer is taken from the petrochemical industry, and it is being consumed by the finished product producer, who are actually producing the final object, polymeric object. And there must have some processing techniques, and all processing techniques of polymeric object, that is based on their thermal behavior, how thermally it is behaved. So you have to define, you have to set a particular operational temperature, operating temperature or processing temperature. So what would be the operating temperature for final processing of polymeric product? That depends on their melting temperature, that depends on their glaciation temperature, isn't it? So what is the difference? Glaciation temperature and melting temperature. So in case of amorphous product, glaciation temperature is becoming more vital. But for crystalline product, melting temperature is more important. So what is the difference? For example, say one amorphous rubber material, its glaciation temperature is sufficiently high, because at normal temperature we are getting rubber material that is rubbery, soft. That means it is belonging below its glaciation temperature, because glass transition means transition from glassy to rubbery, glassy to soft. But in case of plastic at normal temperature, we are getting plastic as a hard material. So its glaciation temperature is sufficiently low, isn't it? So for amorphous material, polymeric material, glass transition temperature is more important. So whenever you are producing any rubbery product and it is being supplied to the customer, you have to mention its glaciation temperature. Again, that glaciation temperature and melting temperature all are dependent on its structure, on its molecular weight, on its crystallinity, also other properties. Similarly, this is the diagram, how the with changing temperature, how it differs. Not only its temperature, it is molecular weight, isn't it? Whenever you are talking about the molecular weight, again another one confusion comes. Because when you are getting one polymer sample, the polymer sample is composed of many polymer molecules. But during production of polymeric molecules, it is almost impossible to produce all the polymeric molecules of equal molecular weight. It is almost impossible, you can say. And for commercial production, it is obvious. But whenever we are talking about the molecular weight, because customer is always demanding their target molecular weight, we need this molecular weight. And that unit should be expressed in terms of not absolute molecular weight, but in average molecular weight. Sorry, just a minute. Not absolute molecular weight, this is average molecular weight. So average molecular weight, how can we average it? How can we make the averaging process? What would be the averaging process? Isn't it? There are several techniques of averaging the molecular weight of polymeric product. And when the polymer sample is given, it will have different molecules of different molecular weight. May have. But what kind of product, how can we make its quality? How can we classify it? How we can give the gradation of the product? Because suppose two producers are there. Two petrochemical industries are there, and I am the consumer. I want high density polyethylene of molecular weight 1 lakh. Average molecular weight, average. So both are agreed to provide that product. So both producers can supply me 1 lakh average molecular weight product of high density polyethylene. But again, question comes, which one will be superior? So one second parameter is required. That second parameter is not only average molecular weight, but also I need to know about its distribution. Suppose 1 gram of polymeric sample is having 10 molecules. One sample is having, both the samples are having 10 molecules. One sample is having 10 molecules. One is having molecular weight 2. Another one is having 3. Another one is having 4. Another 2 molecules are there for molecular weight 5. Again, another one is 7. So ultimately, we are making its average is 5. Similarly, the another one sample, where also 10 molecules are there, out of which 4 molecules are having molecular weight 3, another 3 molecules are molecular weight 5 or 6, and another 3 is having molecular weight 5, another one is having 4. So in that case also we are getting the average molecular weight of 5. So both samples are giving the polymer molecular weight 5, but distribution is different. One distribution was started from 2 to 9, another one distribution was started from 3 to 6. So obviously the second product will be acceptable. Because why? Because low molecular, because polymer, the behavior of the polymer molecule towards the temperature, towards any other operational parameters, that will be entirely dependent on its molecular weight. And particularly it is more significant, its behavior towards the thermal application of the temperature, isn't it? So obviously we always need, we would expect the polymer product with the lowest molecular weight distribution. You see, these are the effects of molecular weight on polymer properties. Molecular weight and molecular weight distribution. Molecular weight increase, its strength will be increased. Molecular weight, if the molecular weight increases, how far the material can stretch before rupturing. Means elongation. Mechanical properties are tensile, elongation, these are all dependent on its molecular weight. Not only that, solubility. So there is a big significance, there is a high significance of molecular weight in every steps of polymer operation or polymer processing. Commercial grades are graded in this way. You see, this is the molecular weight versus the property. Different three properties are mentioned here. One is melt viscosity. Melt viscosity is one of the important parameters because all polymeric product is finally processed in thermal application, under thermal application. So, when the final shape of product is given by using a suitable mold. So, in the mold cavity, thermal application in the almost in molten state. So, the flow characteristics of the molten polymer inside the mold cavity, that is very vital, because otherwise if the flow is insufficient, then the product defects will be generated, surface defects will be generated. So you have to ensure that I need that much melt flow index. So commercially, when we are talking about the properties of polymer, these are graded in this way. You see the molecular weight, the polymeric material, they are behaving like this. The melt viscosity is changing with molecular weight. Impact resistance is changing in this pattern. Tensile strength is gradually increasing. So all are increasing with increasing molecular weight, but the pathway is different. So how can we identify our objective? How can we identify our targeted region? So in this way, this shaded area, this one is considered for the commercial gradation. Yes, we are talking about molecular weight. The molecular weight, average molecular weight. There are several processes, there are several techniques there for calculating the average molecular weight of the polymer. One concept is their number average molecular weight. Another concept is there for weight average molecular weight. Third concept is there particularly for commercial grade, that is MZ. And also the molecular weight is calculated on the basis of the viscosity, because you know viscosity parameter is directly dependent on the molecular weight of the polymeric product. So different concepts are there for calculation of average molecular weight. Number average, you know number average means, for example, just you see number average, say M1 is the molecular weight of ith polymeric chain. Ni is the number of chain of molecular weight of Mi, and Wi is the weight fraction of polymer chains with molecular weight Mi. So in that case, we can get the average by arithmetic, by taking the arithmetic average. Arithmetic mean average, you see, Wi is summation of Mi-Ni divided by summation of Mi-Ni is basically Wi. Mi-Ni is basically Wi. Mi-Ni, I may be 1, 2, 3, 4, 5, 6, up to N, isn't it? So in this way, the averages are being calculated. Number average, this is the formula. Molecular weight average molecular weight, this is the formula. Summation of Wi into Mi, that is, and Wi means Ni Mi is Wi. So Ni into Mi square divided by summation of Ni Mi. Viscosity average is this. Not only that, that one thing is there, that the polymeric sample will have several polymer molecules of different molecular weight. So what would be the distribution? That is more important also. And that's why all polymers are called as polydispersed by nature. So we have to check the polydispersity, means what would be the molecular weight distribution. That will be directly reflected on the polydispersity index. And how it is being calculated? It is just the ratio of weight average molecular weight to number average molecular weight. That will give the polydispersity index. And that polydispersity index, there is a scale, there is a scale. In case of condensation polymers, there is a scale of, it is generally it is being maintained around 2. Okay, in case of addition polymers, it is almost below 2, always it is below 2. Techniques are there in the industry to quality control. Before sending their product, they check the average molecular weight, polydispersity index, because those parameters are to be written in the product bag, because otherwise customer will not receive your product. So there is a quality control unit in every petrochemical industry. They check all those parameters: polydispersity index, average molecular weight, melt flow index. Just one simple example I am telling you, so that it could be more transparent to you. Say one sample is taken. This total sample is 5 gram. Out of which 1 gram sample is having the molecular weight 10,000. Second sample, 2 gram sample is having molecular weight 50,000, and another 2 gram sample is having molecular weight 1 lakh. So how can we get the number average molecular weight and weight average molecular weight? Just using the simple formula, you can get it. Summation of NIMI, that is summation of WI. WI means, you see, it is given 1, 2, 2 given, divided by summation of NI. NI is not given. How much molecules are there? It is not there. So how can we get the number of molecules? Weight divided by molecular weight, that will give the number of molecules. So directly we can get that. So thus the number average molecular weight and weight average molecular weight both can be calculated. So it is very easy to calculate polydispersity index. Now come to the process. Process means these are about the products. What would be the characteristics? What would be the criteria for determining different parameters? Now come to how can we maintain that during production, during manufacturing. How can we control that? That is the big thing for an engineer, isn't it? So up to now, characteristics, these can be maintained, that can be recorded by a chemist. But thing is that when an engineer is going to manufacture industrially that particular polymeric product, how they can maintain those parameters and what would be the techniques behind. That is the thing. So whenever the polymers are polymerized in the petrochemical industry, you will find that there are few techniques are there, basic few techniques are there. And if we look back to the history of polymerization process, when initially it was started in the form of bulk polymerization system. So suppose we are going to carry out one addition polymerization. Addition polymerization means where the monomers are taken, unsaturated monomers. We need a suitable initiator system to start the polymerization process. And at the end, when we want to stop the further polymerization reaction, then we have to use a suitable chain transfer agent or short stop agent. So basic 3 things are required. Now you have been given these 3 things and you started polymerization process in a simple vessel. in a simple vessel. In a batch process, say, I'm just showing you, this one is the vessel. Okay, so you added monomers, you added initiator, and you have to add chain transfer agent after some time. Okay, but thing is that how can you operate it? Addition polymerization, as I mentioned, these are free radical mechanism. Free radical mechanism means always it is exothermic by nature. And again, the rate of polymerization process is very much sensitive to the temperature. And during polymerization process, you have to maintain a certain range of temperature. Particularly, it is more suitable if it is you are capable to maintain a certain particular temperature. But every step of process, every stage of growth, temperature is increased because exothermic, free radical mechanism, exothermic reaction in every steps, it is temperature is increased. But you have to maintain the temperature at a particular range. How is it possible? So you have to provide a suitable chain transfer system, chain transfer arrangement with the reactor, isn't it? So actually it is being practiced that a suitable chain transfer arrangement should be provided during polymerization process. And I am talking about bulk polymerization because only monomer is there, initiator is there, and chain transfer agent or short stop agent is there. Not only that, with the growth of polymer, viscosity of the mass, that is also to be increased. That is also being increased with the time. So the viscosity is increased because how the heat transfer was operated, heat transfer process was executed by providing a suitable agitator. Agitator system is there and whole the mass is being agitated and one cooling jacket is provided, or sometimes you will find that cooling coil is inserted. So whatever the system is there, that should be operated smoothly. So when the temperature is increased, you see that heat will be dissipated by the circulation of cooling water through the jacket. Okay, but it is possible only then if the inside mass is well agitated. But once the viscosity goes very high, obviously with time the molecular weight of the polymer will be gradually increasing. One time will come, viscosity will be sufficiently high, and that impeller is not capable to agitate whole the mass uniformly inside. Then actually problems will be started. Heat transfer problem will be started. At different zones, heat will be blocked, and the blocked zone, as the temperature is more, then the rate of polymerization in different blocked zones will be high. So the molecular weight will be increased at that particular zone. So you cannot be able to maintain the uniformity of the molecular weight. That is the big issue in bulk polymerization system, isn't it? So what happened? This is the arrangement, you see. Generally this is the arrangement. Gases are coming out at high temperature, is being condensed. Gases means mainly monomer gas. It is condensed, liquefied, again it is taken back to the reactor. Okay. So that problem of heat transfer in bulk polymerization system was addressed by providing another one system. This is called solution polymerization system. Because in bulk polymerization no solvent was there. So in the next system, that is when a solvent means solvent to the monomer, solvent to the polymer also, solvent to the initiator, and solvent to the short stop agent or chain transfer agent. So you initially take the solvent into the reactor. Then you add monomer, start agitation. All monomer goes into the solvent, will be solubilized. Then you add initiator into it, and initiator is also soluble into that solvent. Okay, so polymerization will be started. Then you add chain transfer agent, short stop agent, so that it will be again solubilized into it and it will stop further polymerization process, so that at your desired molecular weight level you can terminate the process. So the problem of heat transfer is completely solved only by using a suitable solvent. But another problem was arised, because in most of the cases the consumers, they are taking polymer in solid state, but at the solution polymerization system the product is coming out in the form of solution. So another one additional unit is to be provided there, where you have to evaporate all the solvents and polymers are to be isolated in the form of solid. Additional cost is involved there. Industry cannot sustain by providing additional cost into it. So that is a big issue. Yes, for some cases it is advantageous, where the consumer or the consumer, they are using the product polymer in the form of solution for surface coating industry, adhesive industry. They are utilizing product polymer in the form of solution. In those cases, it is advantageous. But in other cases, most of the cases, it is disadvantageous because additional cost is involved there. Okay, so the third system is introduced. Third system is introduced. You use one non-solvent, not solvent, non-solvent, non-solvent to monomer, non-solvent to initiator, non-solvent to chain transfer agent. You use it. Simply water is used. Water is non-solvent because monomer is organic material, isn't it? So organic material. Simply water is used as non-solvent. Cost is low. So what will happen? You put water into the reactor initially, then you put monomer, say liquid monomer. Liquid monomer is used, liquid monomer is added into it. Start agitation. And you just increase the RPM of the agitator. What will happen? Monomer is liquid monomer, organic material. This is, you can consider it as just oil. So if you put oil into the water, what will happen? Just agitate it. The oil will form small droplets. You add initiator into it. Initiator is also insoluble to water, but soluble to monomer. So that initiator will enter into the monomer droplets. Okay? Chain transfer agent. You add it. It is also insoluble to water, but soluble into monomer. That will also enter into the monomer droplets. Now you just see, individual monomer droplets will function just as a bulk polymerization system. With the time, with the progress of time, all monomer will consumed by polymerization process, and individual monomer droplets will be converted into a particle, individual polymer particle. This one is suspension. But thing is, then another one additional component is required to add there. That is, the individual monomer droplets are to be stabilized in the system in the form of suspension. So that's why one surfactant, a suitable surfactant is to be used just to stabilize the droplet. And not only that, and the end of polymerization process, the product polymer particles will be also stabilized in the system in the form of suspension. And when it is coming out, and in most of the cases it is carried out in a continuous process, and continuous process is using a suitable CSTR, continuous start tank reactor. So continuously monomer is fed into the reactor and continuously product is coming out in the form of slurry, polymer slurry. And separation of solid polymer is very simple, just by filtration. Just you provide one filtration device, all polymer particles will be separated from the slurry. And that water can be again reused in the system. Very simple. And it is becoming economically so feasible, everybody is adopting this process. Only one thing is there, problem is there, was there, that is the particle size. When you are producing polymer particle size, that should be uniform. Because when it is reprocessed, means when it is sent for further processing, for making pellets, for making final polymeric object, then again a suitable processing techniques, a suitable processing technique is to be adopted, where by the thermal application it is further processed. So it's melting, that should be uniform. But once the particle size is not uniform, then the further processing you cannot ensure. So that is the only issue of the suspension polymerization system. So in the a minimum modification was made. A simple modification was made on suspension polymerization process, which is called emulsion polymerization process. All are same. All are same as suspension polymerization. Only two differences are there. One difference is there, that the initiator which was taken, which was selected in suspension polymerization process, which was soluble to monomer, not soluble to water. But in this case, in emulsion polymerization system, it should be soluble to water, not soluble to monomer. Means monomer insoluble initiator is to be selected. This is one difference. Second difference is the amount of surfactant is to be used here some extent more than the suspension polymerization, because these surfactant molecules are playing a vital role during the course of polymerization process. What is that? How much amount of surfactant is to be used in emulsion polymerization system? A particular limit is there. A particular limit is there which is called critical micelle concentration, because you know surfactant molecules means surfactant molecules has two parts. One is polar and another is organic part. Polar is hydrophilic by nature. So you see, this is surfactant molecules. This is surfactant molecules. This is actually polar. So that's why they are tending towards water. And the organic part, tails are organic part, they are just gathering a particular point. So you have to ensure that the concentration of surfactant will be at that level, so that they can produce these kinds of aggregation, which is called micelle. And that amount of concentration, that amount of surfactant is called critical micelle concentration. So for execution of emulsion polymerization system, the concentration of surfactant amount should be more than the critical micelle concentration to ensure the micelle formation. So once the micelle is formed, that is, you see the aggregation of surfactant molecules, these are the polar part which is tending towards water, hydrophilic by nature, and the tail parts are organic. So they are producing an organic medium at the core of the micelle. Monomer is organic, that monomer will be solubilized into it. Okay? And initiator, this is soluble into water, insoluble to monomer. So there is no initiator inside the monomer pool. It is actually residing at the periphery of the micelle. So the polymerization will be started from its periphery. Okay, so gradually polymerization will be continuing, and gradually the inside monomer will be consumed with time. Once the whole monomer is consumed inside, then from the surface, from the bulk, another monomer or another monomer droplets will be diffused into it. Okay, so in this way, the final polymer particle that is being controlled and that is being maintained uniform so far. And you know what is the difference of suspension and emulsion? That is only difference in their particle size. Okay, so it is becoming more, you see, this is the picture where inside the micelle the polymer chains are gradually generated and being increased. And how can we isolate the product polymer from the system? From suspension it was very easy, just by filtration. But in case of emulsion polymerization, how can you separate the product? Because how from the emulsion process, how the product polymer solid is separated? By coagulation. By coagulation, just putting a suitable electrolyte into it, the solid polymers are coagulated and just by filtration it is separated. Isn't it? So different important, very commercially important products are being separated. Plastic, PVC. PVC, you know, the PVC, polyvinyl chloride product is utilized for multi-purposes. Multi-purposes. So one time was there when the PVC was popularly used for electrical isolation purpose. Isn't it? But that product should be produced in suspension polymerization, not emulsion grade. Emulsion grade PVC cannot be used for electrical isolation. Why? Because in emulsion process, the surfactant molecules are used in more quantity. And if the residual surfactant molecules are there, present there, then electrical isolation, complete electrical isolation is not possible. Isn't it? So otherwise the PVC produced from the emulsion process is popularly used for making irrigation pipes. One unit is there in the Chennai. When I worked actually for around 6 to 7 months for a emulsion polymerization unit. They are using that emulsion grade polymer PVC. They are actually for making it as a surface coating purpose. These are the advantages, disadvantages I have already mentioned. Okay, so this is about the product polymer and its polymerization techniques. So if you have any question, you can mail me and I can give the answer. Thank you very much.